All right, guys, let's discuss the answers from last week's homework, guys. Today we're going to be doing exercises today only, because quite a few of them, they said they have something to do. And then, hey, Charmaine, you guys started your exam already, or only starting from June onwards? Charmaine? Oh, Charmaine, are you there? Okay, anyways. Yeah, guys, check. Oh, you were talking. Oh, you were replying on the chat. Why don't you just say something? Okay, anyways. Yeah, let's go through these questions together real quick. If you look at this question here, quite a straightforward one. Uh, they're basically testing about linearity and sensitivity again, guys. For those who have forgotten, once again, I want to remind you that sensitivity is basically just ability to measure small changes, and range is basically the minimum to the maximum, and linearity is basically equal spacing between each and every one of the readings here. Today, if you look at this question here, it says that X and Y are liquid in glass thermometers. The scales of each thermometer starts at 0 degrees Celsius. X has a large range, good linearity, and also high sensitivity. Y has small range, poor linearity, and also low sensitivity. Basically, this is a good thermometer, and this is pretty much a shit thermometer, right? So in this question here, they basically ask you to explain what is meant by the difference in their range. Today, if they ask you to define what's the difference in their range, you only need to see this part here, right? If they say that it has a large range, it means to say the temperature reading for X, it could be anywhere from like -20 to maybe like 110 degrees Celsius. If there's a small range here, it basically is a smaller difference between the maximum and the minimum, right? Maybe it could be 20 degrees Celsius all the way until 60 degrees Celsius only, right? Obviously, from here you can see that this is large range and this is small range here. And if they ask you to talk about the difference in their range, right? The simple answer will be X has a wider coverage of temperature. It can measure a bigger difference in temperature compared to Y, right? Or you could say, it doesn't have to be word by word, guys. You could say something like, X has a larger range that can cover more temperatures. Or actually, it'll be the same thing, actually. It's just a different play of words. Anyhow, you just have to get the idea that range is the difference between the maximum and minimum, right? Then you should be able to answer it. You could even say something like, X has a larger difference between the minimum and maximum temperature, where Y has a smaller difference between the minimum and the maximum temperature. That is going to be acceptable as well. You're basically just explaining the difference in their range, guys. All right. Now, after that, if you talk about the difference in their linearity, one has good linearity, one has poor linearity, right? You could say something like X, right? X has equal spacing between each reading, whereas Y has non-linear spacing, non-equal spacing, equal spacing between each reading. Yet again, you're just talking about the difference in their linearity, right? Just mention what you understand, phrase it down in proper words. It should be acceptable as well, guys. All right. Then finally, they talk about the difference in their sensitivity. You could say, like I mentioned, my right, sensitivity is basically the ability to measure small change in temperature, or for small change in temperature, it could mean a large change in the reading, right? So from here, you're going to say that for small change in temperature, change in reading X is more than Y, right? Because for those who have forgotten, right, let's say imagine this starts from 0, right? Then X, if they say high sensitivity, it will be like 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, blah, 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 all the way until here. Here is a 1 degree Celsius difference. For very poor sensitivity, it will go like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? For the same amount of distance, this is 10 degrees Celsius. This is only 1 degree Celsius. So you definitely can say that the small change in temperature change in reading is X is definitely more than Y. For the 1 degree Celsius, it will be this. For 1 degree Celsius, Y would be this. This is X, and this would have been Y. All right. So these kind of questions here is just basically you talking about what you understand between the the difference of their sensitivity, range, and also linearity only. All right, guys. Anyone's got any questions for this part here before I proceed on? All right. Then moving on to the next part here, a thermocouple. It is quite sketched up, but you don't need to refer to this diagram. I think we've done enough exercises to know what a thermocouple looks like, right? A thermocouple always have a galvanometer. Make sure you label it. You'll have metal X here. You'll have metal Y here. You'll have a hot junction and you'll have a cold junction. Guys, make sure that you label it because I think they ask you to sketch a labeled diagram, right? Draw and label a sketch of the arrangement here. You must label it, galvanometer, metal X, or you could even say like iron, and copper, right? Or copper, steel, or constant, iron, whatever it is, it doesn't really matter as long as it has two metals and a hot and cold junction. Then ultimately, you get free 3 marks here. All right. Then finally, the last part here, the temperature of the liquid is changing rapidly. Explain why the thermocouple is able to respond quickly to this rapid change. Like I mentioned many times, guys, a thermocouple has mainly 2 main advantages, right? The first advantage is definitely it has a large range. The second advantage is definitely it has rapid response. In this question here, they are asking you to explain why the thermocouple can have rapid response. And if you think about it, I actually mentioned this in class before as well. How do thermocouples actually measure temperature? They actually measure temperature through the difference in the metals here, right? In other words, you could say that it is the expansion of metals that is causing the reading on the thermocouple here, right? Today, we know for a fact that thermocouples will respond much quicker because these are metals. Thermometers, guys, they use liquid for them to read the temperature difference. And we know for a fact that metals have much lower specific capacity compared to water or liquid or whatever. Generally, they have a much higher specific capacity, meaning to say more energy is needed, whereas less energy is needed here, right, for the same amount of temperature change now. So if I were to structure this answer, right, I'll say something like thermocouples use metals which have much lower specific heat capacity to measure temperature. You have to understand what is going on here, guys. It is basically a thermocouple measuring with metals, guys, which have much lower specific capacity. And that is the keyword. Okay. Okay. All right, then moving on to the next part here. Define the specific capacity of a substance. I've mentioned this many times, and you will definitely see this a lot in your IGCSEs, guys. They will always ask you to define something which is already in the formula. And when they ask you to define something in the formula, what do we do again in terms of the formula? Natalie, what do we do if we're asked to define these kind of specific questions definition? What do we do in terms of the formula first? Oh, hi, Jerry. Welcome. What do I mean by definition of the formula? And weren't you here last week? Were you here, right? Use the formula to, yeah, you're supposed to use the formula to describe. So first and foremost, the formula is what again? Yeah, make C the subject. C will be equals to Q over M theta, right? From here, if I'm asked to define it, how do I define this? Specific heat capacity is defined as the energy needed to change. What is this? 1 kg of a substance, yeah, by 1 degree Celsius. Excellent, guys. Always remember you're supposed to define it according to the formula itself, guys. Specific heat capacity is the amount of energy needed to change 1 kg of a substance by 1 degree Celsius. Okay? Specific capacity is the amount of energy needed to change 1 kg of substance by 1 degree Celsius. Quite a standard question, a pretty damn standard answer. Make sure everyone knows how to do this, guys. Very, very important. Okay. Then after that, moving on to this next part here, which is essentially calculation. Figure 4.1 shows the cylinder of aluminum heated by an electrical heater. The mass of the cylinder is 800 grams. Obviously, I'm going to change it to 0.8 kg first and identify that this is mass. The heater delivers this amount of energy, which is obviously your heat energy, right? And the cylinder temperature increases by 12 degrees Celsius. This is obviously your theta, right? Then I ask you to calculate the value of the specific capacity of the aluminium. C will have been equal to Q over M theta here. Press everything into your calculator, making sure that the units is the same, right? And you will have gotten something. What's that something? 906. You'll get 906. What's the units of specific capacity again, Charmaine? Joules per kg, are you sure? Yeah, this is joules, right? This is kg, this is degree Celsius, so your units must be joules per kg degree Celsius, guys. Always remember that your units should not be memorized. It should be derived directly from the formula itself, guys. You know that energy is definitely in joules. You know that mass is definitely in kg. And you know that theta is definitely in degrees Celsius. That's why you'll get 906 joules per kg degree Celsius. And always remember, it's supposed to be 3 significant figures. Anything more than that, it's definitely wrong. And the minimum is 2 significant figures as well, guys. You have to be careful with that as well. All right. Then finally, the last part here. Oh no, it's not the last part. I lied. Okay, this next part here is talking about thermal capacity. Jen-Lim, what's the difference between thermal capacity and specific heat capacity again? Jen-Lim. Oh, hey, unmute yourself. Why do you guys have to keep typing? Do you guys have like a...
I think that like specific heat capacity is the amount of heat energy needed to increase 1 kg of substance by 1 degree Celsius.
That's specific heat capacity.
Yes, and then thermal capacity, I'm not sure.
Okay, if you refer back to my notes, I think I told you this, right? You see here, what did we mention last week? I said that the main difference between thermal capacity and specific capacity is that one is missing one specific thing, right? What is this thing missing compared to here? Do you still remember?
There is no mass.
Good, there is no mass. In other words, Q equals MC theta is specific capacity, right? Q is equals to thermal capacity times theta here, right? It is essentially just missing the mass component only, right? So if I make thermal capacity the subject, it will be Q over theta, right? Thermal capacity, always remember, guys, is just missing the M component. That's why it's not so specific. This one here is like heat capacity. This is specific heat capacity, right? Remember that, guys, missing the M component. Very important because it kind of rarely comes out in your IGCSEs. So what happens is students, they usually lack the practice for it. And in the end of the day, they actually forget how to do it. So thermal capacity is equals to Q over theta here. From here is essentially just 8,700 divided by 12. Press that into your calculator and you'll get 725. Exactly, 725. What's the units as well, Jendim, for thermal capacity?
Joules per degree Celsius.
Good, excellent. 725 joules per degree Celsius. Good job, Jen. All right, then finally, this last part here is very important. They always ask you to state and explain a method of improving the accuracy of this experiment. Now, guys, I don't know if I mentioned this before, but let me mention this right now, okay? You know that in terms of anything related to heat experiments, all these calculated values are always like the best case scenario, you know. In reality, if I were to conduct this experiment using the exact same parameters, like 800 grams, 8,700 joules, and 12 degrees Celsius, right? I won't be able to calculate this amount, you know. This amount is like the best case scenario. Why? Because using this formula here, right, it's like simplifying the whole thought process. You know, it's like all external factors are kept at bay. Right? We don't care. We're like ignoring the problem. You know, in these experiments, right, we're assuming that however much energy is supplied from the power pack will be fully converted to this heater, and however much electrical energy is converted to this electrical heater will 100% be converted into heat energy, and however much heat energy is supplied to this heater is exactly supplied into this aluminum cylinder here, which somehow magically just raises the temperature exactly of the thermometer. But in reality, you know, that is definitely not going to be a case because of efficiency problems, right? In terms of efficiency problems here, what's going to happen is, let's just say for ease of calculation, 1,000 joules of electrical energy is converted here, right? Before it even reaches the heater, probably like 100 joules of it is lost as heat to the surrounding already, right? So there's only 900 left here. Then this 900 is supplied to this cylinder here, okay? But this cylinder won't absorb everything, it will only absorb 800 joules. Why? Because some heat energy is actually lost to the surrounding as the temperature continue rising. And among this 800 joules of energy that was supposed to give a reading to this thermometer, right? Maybe only 700 joules of it is supplied to the thermometer. The rest of it is just like dissipated out of the cylinder straight away already. So in reality, whenever we're dealing with all these kind of heat related questions, guys, anytime that temperature or heat is involved, right, they always like to ask this question in your IGCSEs. They'll always ask you to explain a method to improve the accuracy of the experiment. And the standard answer will always be, in order to improve anything that is heat related, you want to prevent all this energy from being lost to the surrounding, right? And the most basic way to prevent all this heat from being lost to the surrounding is adding a layer of insulation. You could add a layer of insulation around the cylinder. You could put a metal cap, or not metal cap, like a wool cap or container or whatever onto it. Then it will prevent more energy being lost to the surrounding, right? So keyword guys, here, the key idea here is that you need to understand that heat will always be lost to the surrounding. The only way to improve anything that is related to heat related questions is to prevent heat loss. And the only way to prevent heat loss is to add layers and layers of insulation to any heat related experiments. Okay, so from here, you know, if I ask you to state and explain the method of improving the accuracy, I'm going to first put my statement on. Wrap a layer of insulation around the cylinder, the aluminum cylinder. And my explanation is obviously because to prevent heat energy being lost to the surrounding. Okay. This is quite a standard question with a very standard answer, guys. You all must know how to do this. Every time you talk about anything heat related, straight away you think that the calculation is assuming perfect world scenario. In reality, it will never happen that way. So in order for me to prevent more heat loss, so that the experiment becomes more accurate, is to just add layers of insulation. Okay. Yeah, before I move on, anyone's got any questions from this part here? Excellent. Yeah. So you see the next question is exactly the same question as well. State what is meant by specific capacity. Same thing lah, always the same answer. The amount of energy needed to change 1 kg of a substance. Standard question, standard answer. Nothing much to talk about here. Then the next part here is going to be basically calculation. All right, basically, if you look at this question here, a student carries out an experiment to find the specific heat capacity of aluminum. He uses an electrical heater and thermometer inserted into separate holes in the aluminum block. The following data is obtained. The aluminum block is this, so I identify this as mass, the power is this, the time taken to heat is this, the initial temperature to here. So the difference is essentially 21 degrees Celsius, right? 21 degrees Celsius. I write it down here. And I identify that this is going to be the data. First and foremost, I ask you to calculate the specific heat capacity of aluminum, right? Specific heat capacity only has one formula, Q equals to MC theta, right? From here, if I'm looking for specific capacity, it will be C equals to Q over M theta lah. And this is when you stumble upon the first problem. You're like, oh, if I'm supposed to look for this, I should be given this, I should be given this, and I should be given this. But right now, looking at the scenario here, I only have the mass component and the theta component. I don't have the energy component here. But in place of the energy component, it gives me the power and time component. From here, if you remember your formulas correctly, power times time is equals to energy, right? Because power is actually equals to energy over time. So power times time is equals to energy. From here, I'm going to find my energy component by taking the power multiplied by the time, which will be how much? What energy? 399. 39900 joules, right? 39900 joules is the amount of energy. From here, I can plug this in, I can plug this in, I can plug this in here, and press everything into the calculator. Basically, divide by 2, divide by 21, right? And you'll get exactly units of 950 joules per kg degree Celsius, guys. You'll get exactly 950 joules per kg degree Celsius. Anyone had difficulty doing this question? Anyone can't do this right now? Anyone like lost or anyway? Anyone having any problem at all? Okay, then finally, the last part here. In experiment B, no attempts is made to prevent loss of thermal energy from the surface of the block. Suggest 2 actions the student could take to reduce the thermal energy from the surface of the block. Everyone has answered me once already, right? Jawei, it's your turn next. What action do you think you could do so that you can prevent thermal energy loss? Give me 2. Cover with insulating material. Yes, definitely number 1. You're going to cover the cylinder with insulating material. Wrap the cylinder, right? Wrap the this is a cylinder, by the way. Yeah, aluminium with insulating material. How about the second one? What else can I do to prevent energy loss to the surrounding besides wrapping it? Jie, what do we do? Lid, excellent. You put the you add insulating material on the lid as well, right? Basically, you cover the top of the block, right? Add insulating material on the top. Hey, these two are the standard answers, by the way. You definitely need to cover, you wrap the cylinder, right? You basically wrap it around here. Then after that, you add the lid here. For those who have cooked Maggi mee, you definitely put the cap on when you're heating it up as well, right? So that the water boils faster. So that that's because energy is less likely lost to the surrounding, basically. Right. Okay. Then the final part here before we do some exercises today. If you look at this statement here, state what is meant by the specific latent heat capacity, latent heat of fusion of a substance, and they give you 2 marks here. How should I answer this, Charmaine? What do you think the answer could be for this one here? First and foremost, it is the formula, right? So making it the subject first will give you what? Q equals to ml, good. So making which one should we make the subject? What should be the subject, Charmaine? Q, no. We want L to be the subject, right? L will be L will be the subject, then it's O, Q, O, M. From here, just looking at the formula itself is not good enough, right? Because just looking at the formula here, we know that latent heat of fusion is the amount of energy needed, to change 1 kg of a substance from what to what? And then you change the state of 1 kg of a substance. And there's one more extra very important keyword that I've mentioned last week. Very, very important. It's related to the graph one. Wow, very good, Jie. No, not to evaporate. It's without any change in temperature. Remember or not? The graph yesterday, not yesterday, right? Last week, we talked about it, right? Why is there flat lines here? It's because the energy is absorbed by the bonds, right? If they're absorbed by the bonds, it means to say no increase in temperature is basically used to break the bonds. No increase in temperature, break the bonds. Increase in temperature, break the bonds, and so on and so on and so on. These are the keywords, guys, in terms of latent heat of fusion. So it is basically the amount of energy needed to change 1 kg of a solid into liquid without, keyword here is without any change in temperature. Okay. And then from here, it's basically just the calculation. Ice cubes of total mass 70 grams at 0 degrees Celsius are put in a drink of lemonade of 300 grams. All ice cube melts at 23,000, blah, blah, blah. And the thermal energy transferred from the lemonade to the ice, the temperature of the drink is 0 degrees Celsius. Calculate the latent heat of fusion of the ice. From here, very straightforward, right? first and foremost. We're definitely going to change this into kg, right? But I've seen the mark schema, guys. You could leave this in grams and then specify later that your answer will be in joules per grams. That is acceptable as well. But of course, if you were to use 70 in your calculation and then your units, you you follow joules per kg, right? Then it is obviously going to be wrong, right? So from here, right, you're basically going to say something like latent heat of fusion, L will be equals to Q over M. From here, it will be what? Q is 23,500. Your mass is just 70 only, right? You're going to use 70, guys, because it's the ice that we're looking at. We're not looking at the lemonade, right? Latent heat of the ice, latent heat of fusion of ice, 70. So you press that in your calculator, you're going to get some very weird answer, I assume. 335, 336. 336. You're going to get 335.7, but of course, you're going to round it up to 3 significant figures. So you're going to get 336 joules per gram. For those who have changed it into kg, which usually I recommend, right? I recommend changing it into kg. For those who have changed it into kg, you'll get a totally different answer, which is going to be even bigger, right? But joules per grams is acceptable as well. Then after that, the next part here, thermal energy that causes the ice to melt is transferred from the lemonade as it cools. The loss of thermal energy causes the temperature of the 300 grams of the lemonade to fall by 19 degrees Celsius. This is going to be your theta. This is going to be your M. Calculate the specific capacity of the lemonade. C will have been equals to Q over M theta. Here it will be like 23500 divided by, yeah, probably this one I'll change it into kg, 0.3 multiplied by 19, right? So press that in your calculator. 23500 divided by 0.3 divided by 19. You're going to get 4120. 4120 joules per kg degree Celsius, guys. It's going to be like 4120 joules per kg degree Celsius. Okay. And then finally, the melting ice flows on top of the lemonade. Explain the process by lemonade. Oh, you guys most likely can't do this yet because it's actually convection current that's causing the hot air to rise up and the cold drinks to go down, guys. But yeah, this is in the next chapter, which is probably in 2 weeks' time. Sorry, I mean next week. We're gonna do the next chapter next week, guys. So yeah, which is just in time for the KDU exam to cover as well. Right. So from here, just basically, yeah, just copy this down. I haven't learned this yet. Like convection current causes the hot liquid, which is less dense, to float up. Just copy this down first. You haven't learned anything yet, so it'll be a bit hard to explain. All right, everyone. Anyone's got any questions for this part here or not? Anyone's got any questions from everything we've done? Good. If there's no questions, let me select a few questions for you guys to do, and everyone tell me the answer of how to do it. Starting off with this question here. How long do you need this format question? 5 minutes, huh? Hey, 5 minutes, everyone. Start doing this question and tell me what's the answer. PM me your answers as well, guys.
Ladies and gentlemen, welcome.
Oh, Jerry, excellent. That's fast and accurate. And you some more say you're not good in physics? You're lying to me? Don't say that, okay? That's a sin to say that. Very good, Jen Lim. That's the correct answer. Yes, Natalie. Oh, 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 okay. Shermaine, are you still doing the calculation? Oh no, that's wrong, Charmaine. How do you get 22.7? Okay, let's go through this question together first. First and foremost, Charmaine, I want to ask you, right, when you were doing the calculation, did you use 4 as your time? When you are doing the calculation, how can it be 4? How many times I tell you this already, Charmaine? This must be in seconds, right? I think if you change this into seconds, you should be able to get the answer, which is times. So basically, if you identify all your information here, you're looking for temperature change, right? Which is equals to theta law. Theta would have been Q over MC, right? From here, you don't have energy mass, so it's going to be power times time is equals to MC law. From here, it's just 370 multiplied by 4 times 60, because it is always in seconds, right? Divide by your mass, which is 5 kg, divide by your specific velocity, which is 420. Press everything into your calculator, you should be able to get 42.3 degrees Celsius. Right? Make sure you always remember your units are very important, especially when you're doing the calculation, guys. That's why I always tell you guys to do it everything into the standard form. Okay? Okay. Then yeah, let me find one more question, one relatively harder question for everyone to do. Yeah, is it this one? Yeah. Hey, everyone do this and tell me what's the answer. Oh, 5 minutes as well, guys. Jermaine, that is the wrong answer. Try to check your calculation again. Oh, yeah, that's the correct one already. How do you jump so fast, by the way? What went wrong? Oh, yeah. Yeah, notice you always put the wrong calculation in your calculator, Charmaine, especially when I was with you that day as well. Try to be careful with your calculation, yeah, Charmaine. I think it's been happening quite often already, right? Yeah, just be careful. 168, bro. There's not even the answer there. How can the answer be 168? Bro. Where is 168, bro? Jen Lim, I'm surprised you haven't given me an answer yet. Are you stuck, by the way? Yeah. You guys attempt it for like maybe 2 more minutes. Then after I'll tell you how to do. This question is a bit tricky. So yeah. No, that's wrong. Why is everyone getting that answer initially? You're not supposed to use the 18 because 18 grams of ice remains unmelted. The keyword here is unmelted. So how much actually melted? Okay, guys, let's go through this. Jen Lim, you're actually very close already. Just that you didn't read the question properly, probably. Okay, now if you look at this information here, right? First things first is I noticed that the heat capacity is already joules per grams degree Celsius, right? So if I see that the answers are all in joules per grams per degree Celsius, no, that's not right as well, Jerry. How did both of you guys get A as the answer? Very good, Natalie. That's the correct answer. The answer is actually supposed to be B. Why? Why? Look at this information here. What do you have? It says that 100 grams of water at 25 degrees Celsius is poured into an insulating cup. They say this are indicating that no energy is going to be lost, guys. It's just like a hidden thing. But anyways, 50 grams of ice at 0 degrees Celsius is added to the water, and the water is stirred until the temperature of the water falls to 0 degrees Celsius. 18 grams of ice remains unmelted, meaning to say 32 grams of ice actually melted, right? From here, if I were to draw the diagram now, right, basically there's 100 grams of water at 25 degrees Celsius, and you put like 50 grams of ice at 0 degrees Celsius, and you're waiting for it to melt. At the end of the day, the ice that melted was 32 grams, and the only ice that did not melt was 18 grams here. From here, this situation is yet again thermal equilibrium. The amount of energy that is gained by the ice is the amount of energy lost by the water. From here, I can write down a simple formula like Qi is equals to Q of the water, right? The amount of energy from the ice and the amount of energy from the water itself. From here, amount of energy of ice at 0 degrees Celsius obviously is not going to be MC theta, right? In fact, the question already stated you're looking for latent heat of fusion. It's going to be MLF is equals to MC theta. And here is the tricky part, which maybe some of you guys did. Since you see that there's 2 M's here, right, you're going to assume that the masses are the same. You could have either substitute 100 into the double M's, or you could have substituted 50 into the double M's, or you could, for some ridiculous reason, might have even substituted 18 into the double M's, which is definitely wrong, guys. You need to understand what these M's are standing for. This MLF, this MLF here, right, is basically mass of the ice melted and latent heat of the ice mass. So from here, how much of the ice melted? It was 32 grams, right? And this will be LF, the thing that you're looking for. And the mass of the water is how much? Is going to be 100. Specific capacity is 4.2, and then the change in temperature, it goes to 0, right? So it's 25, right? So from here, it's 100 times 4.2 times 25 divided by 32, guys. And ultimately, you're supposed to get B as the answer here. Guys, you understand what I'm talking about? I think only Jen Lim might have not been able to do this, but do you know what I'm talking about? You know what's going on? Yeah. Which part did you do wrong, by the way? I think you got this part correct, right? 100 times 4.2 times 25 should have been correct. Oh, you didn't do this. You put 18 here, is it? Oh, yeah, GG. That's wrong. Basically, 20. That's even worse. Yeah, but just be careful, guys, when doing the calculation and read the question properly. It's always not as easy as it seems, guys. I need you all to know that it's never as easy as it seems. Always tell yourself that. Okay. Yeah, I think let's do one more calculation question before we end the day. Aha, this one, the perfect one. All right, do this calculation here. And after that, let's end the day. Got anything to do with 20%? Yeah, definitely. It's not there for fun. 57%. What are you looking for? Yeah, that's correct already. Very good, Jandim. That's correct already. You can make a move. There'll be no homework this week. Next week, we're going to move on to the new chapter already. That's correct as well, Charmaine. Very good. Okay, bye-bye. Charmaine, you have earned your freedom as well. You can make a move as well. Bye. Welcome. Yes, Natalie. What percentage? Jewei, 200 over is definitely not gonna be correct, right? How do you get 200 over? Okay, let's go through the answers together. I think, hey, Jewei, you got maths class at maths class, you remember, right? Has Gilbert messaged you already? Yeah, okay, let's go through this real quick. Okay, 5K watts, this is obviously the power, right? So in reality, it's going to be 5,000 watts, right? Only 20% of it is transferred to the water. So 20% of this is how much? It's going to be like 5,000 multiplied by 20 over 100, right? Which is essentially going to be 1,000 watts. How can you use 5,000? They only say the efficiency of 20% only, mean to say only 20% go through, you know. From here, with this power, I think you can find the time already. What's the time? Oh, every hour. This is the time, which is 60 times 60, right? Which is 3,600 seconds. So from here, theta would have been equals to Q over MC, right? It will be power times time over MC, right? Which will be 1,000 times 3,600 divided by the mass, which is 15, divided by the specific capacity, which is 4,200. Press everything in the calculator, you should get 51.7 degrees Celsius. Okay. Read the question properly, guys. All right. Okay. Yeah. That'll be it for today. I'll see you guys next week. Bye-bye.